Okay, so let us begin. This is now lecture 19 of the course. So last time we looked at how single band SFR measurement indicators could be used to predict the star formation rate by measuring typically a luminosity in the X-ray or in the radio and so on. You can also try to measure the star formation rate from X-ray emission. And
Excuse me, sir. I think you have not shared your
I've
screen.
not shared the screen. Yes. So you can also try to measure it from X-ray emission, but X-ray emission is a bit complicated because it is produced by X-ray binaries. It is produced by massive stars and of course by supernovae. So if the star formation rate is high, then you will have lots of massive stars, lots of supernovae, and therefore those will contribute to the X-ray emission. But you have to worry about the fact that X-ray binaries also contribute to the X-ray emission, both high mass and low mass X-ray binaries. These are not related in any way to directly to star formation, and they represent a very big error in the calibration of the SFR. So this was realized a long time ago, but the early generation of X-ray satellites had such poor resolution that you could not separate out the flux from the X-ray binaries and the flux from the star formation related processes. You can get X-ray emission from AGNs as well, absolutely right. But again, as I said, AGNs are easy to identify because all you have to do is take a spectrum of the center of the galaxy. If you take an optical spectrum of the center of the galaxy, in 1 second you can tell whether it's an AGN or not. Okay, it's not a very difficult exercise. So AGNs can easily be taken up. So in most cases, when we talk about star-forming galaxies, etc., we try to subtract out the AGNs from our sample. Right? Although they're important, as we shall see, they play a very important role in feedback processes in galaxies. And so, yeah. So this is a picture of the Sombrero galaxy taken with Chandra, and Chandra has the advantage that it's a very high resolution X-ray telescope. And Chandra came online about 20-25 years ago. Before that, what people were getting was the total flux from each of these X-ray binaries, plus the flux from the hot X-ray halo. So they were measuring the total flux because these were not resolved out. And so they were getting a very highly overestimated X-ray emission. And that was messing up the calibration also, because you want to calibrate from nearby galaxies the X-ray luminosity and the star formation rate. So the whole thing was very, very uncertain. But with the advent of Chandra, you can see each individual X-ray binary. And you can go and measure its flux, measure this flux, measure that flux, and so on. And then subtract out all that flux, and then you will get the flux from this central region, which is the thing that is due to X-rays coming from star formation related processes. And once you do that, everything works fine. And this tells you very easily why resolution is important. With a high resolution telescope, you're able to do this, which you wouldn't be able to do otherwise. X-ray binaries have also been found, ultra-luminous X-ray binaries have been found close to the center of M31. Okay, and these, as you must have learned possibly in your stellar physics course, stellar structure course, are typically binaries which are accreting. So there is a compact object, and it is accretion disk forms around it because its binary companion has filled up its Roche lobe, and material is being fueled onto this compact object. So these are your X-ray binaries, very, very luminous in the X-rays because of the hot corona of the accretion disk. Huh? Sorry? Yeah, these are in M31. They are in fact near the M31 center. So X-ray binaries are so luminous in the X-ray that we can detect individual stars even in out to the distance of nearby galaxies. Not very far. You can't go to the high redshift universe, but in the nearby universe, you can comfortably detect with instruments like Chandra. So this particular image is with the EPIC camera on the XMM Newton telescope. EPIC is their sort of low soft X-ray band image. This is a soft X-ray band image. Yeah. Yes. Yes, but they are very few in number. Because remember, when you're seeing the whole galaxy within, let's say, half a degree or less. But with the Milky Way, even if it has the similar number of X-ray binaries, only one or two may lie along the line of sight. And it doesn't matter so long as you subtract it out. Unless you are studying X-ray binaries specifically, you subtract out everything. Let us say this one binary is in the Milky Way, everything else is in the sombrero. You just have to subtract the flux, that's all. Right. So, okay, so now coming a brief discussion on the seminars. So the seminars are now confirmed for the 26th and 27th of April, Tuesday and Wednesday next week in the morning. Each of you will have 17 minutes to speak with 3 minutes for questions. Okay. Given that there is a large number of students, we may not be able to accommodate questions from the students, but maybe we can take one or two. But they will, so most of your questions will come from your 3 graders, which is Yash, me, and Pritish Mishra. This is how you will be graded. You will be graded for content. Okay, that is 10 marks. And while doing that, we will look at did you place the talk in context? Did you read and understand the paper and any auxiliary papers? I know that you guys are very busy, so we are not really expecting you to go very deep into other papers. But the paper you have chosen, you must have read fully. Did you answer the questions well? Presentation will have 10 marks. Were the slides well ordered? Was the text legible? Were the figures readable? Did you pace the presentation well? Okay, we don't want you to get into, there are people who make a lot of slides and in the last 2 minutes they cover 20 slides. We don't want that. Okay, we don't want you to also say, oh, I'll skip this slide because I don't have time. So that means you have not paced yourself correctly. Was your speech clear and confident? So how you speak also matters. So that will have 10 marks, and timeliness has 5 marks. Full marks for going -4 to +2 of the specified time, but please don't go outside that. Otherwise, you'll start losing marks out of these 5. Right? Yeah. So that is how your 25 marks for this thing will be graded. So we will do it on 2 days. We'll have one session from 9:30 to 11:10. So that will be 5 talks of 20 minutes each. And 11:30 to 1:10, which will be another 5 talks. Now, what I'm going to do is I'll group and order those talks. And what I will do is I'll keep the more specific talks on the second day. The more general talks will be on the first day. And related talks will be together. So for example, I think there are 4 AGN talks. So they will all be one after the other. You should present your talk at a level that your classmates can understand. And you can speak, if you wish, as if you did the work yourself. So you say we did this, we did that. It's okay. You don't have to. You pretend that you did it yourself, and you can assume that whatever has been taught in all the courses that you have had so far is known to everyone. So don't try to explain what a luminosity function is or elliptical galaxy is, and so on. Okay, so we'll move on. I hope there are no questions about this. Are there any questions about the seminars? Now, online or here, I would prefer, if possible, to do it here. Okay? So there are two options. You can bring your own laptop. We can connect it here fairly quickly. HDMI and VGA connectors work quite clearly here. But if for those, of course, there are few people I know who are not even here physically in Pune. Please, you can join online. So yes, we can also do that. Yeah. So you can email, if you email me in advance, then we'll put one laptop here. Yes, you could, but emailing is faster. Okay, because pen drive sometimes it doesn't read, etc., etc. There can be trouble. Email will work for sure. And, I'll make sure I'll need my own laptop, but I'll get an extra laptop and I'll connect it here. So just email it to me. Right. So now we move on to galaxy evolution and the connection between galaxy evolution and morphology. And when we say galaxy evolution, most of the time we're asking how does the stellar population evolve? How does the gas content evolve? And how does the environment evolve? And how does all of this affect the morphology of the galaxy? So these are the sort of central questions that we try to address in galaxy formation and evolution. So it turns out that galaxy morphology, the star formation history, the stellar mass and projected surface density, stellar mass density, are all correlated with each other. This is not totally surprising because we have seen earlier that for elliptical galaxies, etc., where the morphology is fixed, everything else is sort of well constrained. You give two parameters, you can determine almost everything else. So with the advent of the Sloan Digital Sky Survey in the early 2000s, it became apparent that there are two separate populations of galaxies. One is what is known as the red sequence, and the other, which is known as the blue cloud. And in between, so this is a distribution histogram of G minus R color. Okay. So this is your blue cloud, and this is your red sequence. This is your green valley. And this is contours of number density on a color magnitude plot. So the ones which are bluer in color, which means lower values of G minus R, this is your blue cloud and this is your red sequence. Why the blue cloud is not called blue sequence? There is a reason for that. The red sequence is actually a sequence of metallicity. So this spread in the red population is caused by varying metallicity. Whereas in the blue cloud, the variation in metallicity is quite small. There are galaxies here which are most of them are high metallicity, the blue cloud galaxies. So naturally, you will be tempted to make a connection with this color-based distribution and morphology. And in most cases, most of the times you would be correct. So what morphology would this population correspond to? Ellipticals. And this one would correspond to spirals, right? Now, There's stuff in the middle. So we'll come to that in a minute. So this is another representation. So this is also a color magnitude diagram. This is the NUV minus R color instead of G minus R color. And this is the red sequence. Over down here is the blue cloud. Okay. And here in between is the green valley. So what are these green valley galaxies? What could these be? Huh? Irregulars, yes, they could be irregulars, but they could be in here also, in the blue clouds, in the star forming irregulars. Huh? Yes, yes. So these could be galaxies that are spirals that are somehow faded. Okay, they have lost their gas and their star formation rate has come down. So they are no longer blue. Could there be any other way of forming Green Valley galaxies? Sorry? Can increase, yes. So you can rejuvenate ellipticals. So imagine there is a nice high mass elliptical, it's quietly sitting, but a small dwarf irregular falls into it, right? Due to interaction with the environment. In that merger process, because a lot of new gas has come in, there could be a brief episode of enhanced star formation. In that case, a galaxy which is sitting in the red sequence may jump here. So you can have galaxies moving like this into the green valley, but you can also have galaxies moving from the red sequence into the green valley. So these are two ways broadly in which you can. Yeah. So galaxies are well known to divide into two large families, red old ellipticals and blue star-forming spirals. The SDSS has shown that in the local universe, the division into these large families happens at a stellar mass of 3 into 10 raised to 10 solar masses. So if you have a galaxy that is more massive than 3 times 10 raised to 10, then it is more likely, it's not 100%, but it is more likely that it is a red galaxy. If it is a low mass galaxy, it is more likely that it is a blue galaxy. Right. So you can make a plot like this, which is called as the galaxy main sequence. Okay. It is not as fundamentally important as the HR diagram, which is incredibly useful and important, but this is less important, but still useful. So what we've done here is we plotted the number of stars forming, the star formation rate. This note that both axes are log scale. Okay, so the log of the number of the star formation rate and log of the number of existing stars. If you do that, then most star forming galaxies lie along a straight line, which is referred to as the main sequence. There are a few galaxies which lie on a line which is parallel to this main sequence and above it. These are what are referred to as starburst galaxies. So they have, from what you would expect from their general morphology and stellar mass, etc., they have a much higher star formation rate. These are very often associated with galaxy mergers. So there is, let's say, a nice spiral galaxy, but it undergoes a merger with another gas-rich spiral galaxy, and it jumps for some time into the starburst category. So M82, for example, is a merging galaxy like that. It's a starburst galaxy. And the Andromeda Milky Way merger will also produce for some time a starburst, because both these galaxies are large gas-rich spirals. The Green Valley is here in between. As we said, it consists of galaxies either transitioning from here to here or from here to here. And then, of course, down here are the red and dead galaxies. They're typically more massive They could even populate the regions here, but their star formation rate is quite low. Blue point in the, yeah, green point in the, yeah. So see, this is just qualitative, okay? Because if it's right on the border between red and this, you can't really tell whether it's a green valley or, there are various ways of defining these. We won't go into that. Yeah. No, this is just a cartoon to represent, but if you can do this plot with actual galaxies also, and you will get the similar distribution. Yes.
Like here also, on paper, the population of the red galaxies seems like red ellipticals, red spiral they are divided.
Yes.
And it is like 30, 40 galaxies are there
Huh.
in the red elliptical. So how much it is correct to statistically tell that these 30 are showing this property, so all red
will show this property. See, the study that you are looking at has very few galaxies.
yeah.
But if you go and look, I should have written the rep. If you go and look at a paper by Kaufman et al. 2003, which was the paper which first discovered this kind of red-blue dichotomy, you will see that they have thousands or tens of thousands of galaxies. So this study that you are looking at may be looking at a small sample, but that study has been repeated by others with very large samples. So it's a very, very robust observation at this point. Yeah. Okay. So this is the kind of differentiation you can make between low mass and high mass galaxies. So low mass galaxies have young stellar populations. These other ones have old stellar populations. Low mass galaxies have low surface mass densities, at least in the central regions, while the high mass have high surface mass density. So typically you will find that if you're looking at the bulge at the center, it goes up very steeply. You've seen the Dressler's law, goes up very steeply. So you will have high surface mass density. The number of stars per unit kpc square will be very high. And that's not true for disk-based systems because that remains flat. And so the mass density does not, it goes up, but not as quickly as the high mass elliptical-like galaxies. So naturally, these will have a low concentration index. These will have a high concentration index. These will typically have lots of gas. These will have little or no gas. These are what we call blue cloud. This is what we call red sequence. These are generally fast rotators. These are generally slow rotators. This we will typically find morphologically, visually, to be a spiral. This is an elliptical. So if you ask the question, what are the most important factors that regulate this separation? Why do some galaxies become spiral and some galaxies become elliptical? So the most important things seem to be gas supply and quenching. Okay, so how much gas is coming on into the galaxy? Remember, the gas can come in two ways. It can come in through mergers, with a galaxy which brings in its own gas, but it can also come in through accretion. Right? And a method of accretion known as cold mode accretion is supposed to continuously result in infall of gas. We'll come to a little bit about the hot X-ray halos and so on, and how that prevents infall of gas later on in the season. So there is a constant interplay. Gravity is trying to bring in the gas, and feedback processes are trying to drive out the gas. So there is this kind of balance between the two, which regulates whether a galaxy is star forming or quenched. So on the galaxy main sequence, where do you think the Milky Way sits? Where will it sit in the far future? What kind of galaxies are present in the Green Valley? That I think we've answered. So let's look at the first two questions. On this diagram, where does the Milky Way sit? It's not a starburst. No. Huh? It's not in the Green Valley either.
So main sequence.
Yeah, it will sit on the main sequence. It is relatively, number of existing stars, remember, are quite high. Okay. It is not a starburst. So it's not going to be here. It is going to be here somewhere in this region. Right? And towards this right side. It is definitely not towards this side. It is somewhere here. Right? Yes, so it should be a little bit to the right, but not always. In the sense that we have, this cartoon is a bit misleading because it tells you, gives the impression that the number density of these blue points is sort of uniform across all stellar masses. That is not the case. The number of galaxies that you have here are far more numerous than the galaxies here. So at high mass, at low mass, you will invariably have lots of spiral galaxies. At high mass, you will still have a few spiral galaxies, although most will be ellipticals. Right. So Milky Way is going to be here. Where will it be in the far future? So far future, like 10 billion years from now. Huh? It'll be here. So it is going to start here, go up there, become a starburst when its merger is happening. Then the gas gets rapidly used up, lots of stars get created, no more gas is left, and then it falls here. That's the fate of the Milky Way. Yeah. Yes.
So gravity is bringing the rest to are the people processes very high.
Not necessarily. What is happening is, think of it this way. Why do the elliptical galaxies have high mass? Because they were star forming in the past. So they used up whatever gas was there in their vicinity in the distant past. Now they are sitting in places where further gas cannot fall into them. So typically in the centers of clusters. And we know that clusters have a very hot X-ray intracluster medium. So it is very hard for cold gas from outside the cluster to fall into the cluster. But AGN related feedback is also important. Lots of elliptical galaxies have powerful AGN. So when you do your AGN course, you will find one more differentiator, which I haven't listed here, is that the high luminosity AGN are in ellipticals and the low luminosity AGN are in spirals. So the AGN driven feedback is much stronger in ellipticals, and therefore the gas gets driven out more easily. We'll see that. We'll see the hot gas here. So, okay. So this is the question we are trying to look at. What inhibits star formation in the most massive ellipticals? Has star formation stalled in these galaxies because the gas supply has been fully consumed? Okay, that is true. Certainly, whatever gas was there in the early days, lots of mergers were happening, lots of star formation was happening. All of it has been consumed. Or has the gas been pushed to the outskirts of these galaxies by tidal effects or ram pressure stripping, or heated to temperatures that inhibit the gravitational collapse needed to form new stars? So all of these factors are probably operational. We know now for the most massive ellipticals, which sit at the centers of clusters, It is the hot halo, which you see as X-ray emission, continue emission in the X-rays, that prevents further infall of the gas. So here you can see the diffuse emission here. That is the hot X-ray halo. And that is preventing new gas from falling in because it just collides with this energetic gas, high temperature gas. Okay. Yes, yes. Correct. So there is, it's not an absolute thing that, okay, not one molecule is going to reach, but it just becomes harder than if things didn't operate. You're right. I mean, if this were the hot gas has to be sustained. So we'll come to that. So because hot gas is there, eventually it'll cool. Once it cools, then gas should start begin to fall in. Why doesn't that happen? So there must be a mechanism for keeping the gas hot, feedback mechanisms. Okay. So in 2012, about 10 years ago, we discovered a very large hot X-ray halo around the Milky Way galaxy as well. Okay. This is a very nice paper by Anjali Gupta et al. And they did this using the Chandra telescope. Now it's easy to see how you can discover a hot halo in an external galaxy. You subtract out all the X-ray binaries, etc. How are you going to discover a halo in your own galaxy? You're sitting inside the halo. How will you do that?
Sir, all sky survey kind of thing.
Yes, yes. You can't actually do an all sky survey. You will have to take different pointings in many different directions. Okay, but what telescope will you use and what will you look for? See, if you have some object which emits at a certain frequency or a certain line, okay, if there is another source which is emitting at that line and this gas is slightly cooler than that, what will happen? What does the outer atmosphere of the sun produce? Absorption lines, right? So what kind of absorption lines will this gas produce? X-ray absorption lines. So if you have a strong X-ray source in the background, this gas will produce absorption lines in the X-ray band. And what these people did is that they used very, very high transitions of oxygen, I think oxygen 7 or 8 or something like that, highly ionized oxygen transition lines, which are in the X-ray band. And they saw absorption lines along lines of sight to different quasars in many different directions. And they use that to show that there must be a hot X-ray halo, which we are seeing in absorption, around the Milky Way. And they tried to estimate its size and density and things like that. You can't really estimate the size. Okay, you know it's not at very high redshift. That much you can tell for sure, because otherwise the line will get absorption line will be redshifted. Okay, it's not very far. The absorption line is at 0 redshift, so it is in the immediate surroundings of the Milky Way. That much you're sure. But whether it is a dense cloud which is here or a less dense cloud which is much bigger, one can't tell for sure. So therefore, this is just a cartoon. It's very close. It is not redshifted at all. It's broadened. Huh? Source is redshifted
X-ray is
outside. It is a distant quasar whose redshift you know. So it's a hot, it's a strongly X-ray emitting quasar. You need strong continuum X-ray emission from the quasar. The H1 halo typically for a spiral disk galaxy is maybe 2 or 3 times larger. This one they suspect could be about 10 times larger. So it's larger than the H1 halo or the H1 disk, extended H1 disk. No, you need multiple lines. No, you can only constrain it that it has to be smaller than a certain size. Because if the halo were not here, there was nothing around the Milky Way, but there is a much bigger halo further out. Okay, you will begin to see its redshift. And these are very high resolution spectra. So even if the line shifts by a fraction of an angstrom, that can be detected.
is outside.
Yes,
And it is time.
yes.
So that X-ray will also do the redshift.
Yeah. But that is the continuum will get redshifted, no? And any emission lines, continuum, whatever is there in the X-ray spectrum of the quasar, that will be redshifted.
Yeah, so X-ray will not be in the X-ray.
No. It may go from hard X-ray to soft X-ray. The beauty of observing quasars is that they are so luminous over such a wide range of frequencies that your hard rest frame emitted hard X-rays may come to your soft X-rays. This work is done in soft X-rays, so you don't have to worry about that. No. They've just put it to give you the context of size, that there seems to be a hot halo of X-ray gas, hot gas, which is absorbing the X-ray flux from the distant quasar, and it's quite large, is what they've claimed. Yes, so you can, but they're not very well constrained. All of these, there are some degeneracies there, which cause problems. Okay, so what is causing the presence of this hot gas halo? It has to be long-lived. Okay, because we know nothing special has happened in the life of the Milky Way in recent times that it suddenly developed a thing. So there is a tug of war between the pull of gravity and the push of feedback coming from stellar evolution, as well as AGNs, as well as interactions with the circumgalactic media, galaxy encounters, etc. If there is equilibrium, then one can measure the mass of a galaxy or a cluster via hydrostatic equilibrium. The discovery of these hot halos and the characterization of these properties have been very, very unique contributions of high resolution X-ray telescopes like Chandra to astronomy. Okay. So the most important parameter that defines how a galaxy will evolve seems to be stellar mass and morphology. So if you know the stellar mass, if you know the morphology, then the other parameters, although important, are much less important, like the environment and so on. The first manifestation of the relationship between morphology and the environment was observed many decades ago. People had already discovered that if you look at clusters, near the center of the cluster, you almost always find only ellipticals and lenticulars. As you go further out, you begin to see spirals. And as you go far out, far away from the cluster into the field, you see lots and lots of spirals. So this is referred to as the morphology density relationship. So what is shown here is on the x-axis is the log of the rho projected. So it's the stellar mass density, or in this case, the number density of galaxies, not the stellar mass density. The number density of galaxies on some log scale. And on the y-axis is the fraction of different kinds. So over here are the ellipticals, over here are the spirals, and over here are the lenticulars. Okay. So as you can see, once you go from low density to high density, the fraction of spirals drops and the fractions of both ellipticals and S0s goes up. Now, this was discovered by, or observed in a very systematic way, not discovered, by Dressler in a classic paper in 1980. He took 6,000 galaxies in 55 clusters plus 15 field regions. He recorded positions and local projected galaxy density. So what he said was, he measured, how do you measure galaxy density? You could measure the distance to the fifth nearest neighbor or something like that. If the distance to the fifth nearest neighbor is very small, that means you are in a high density region. If it is very large, then you are in a low density region.
I'm doing a project field.
Yes.
So it could be that the density in this side, the galaxy actually in this side, are very distant.
Yes.
And when I'm doing projection, it is coming near to me.
Yes. So the probability of getting unrelated galaxies in that narrow field of view is very small. So suppose I'm seeing a cluster and I see 10 galaxies there in that cluster. Maybe one of them is, as you say, either in the foreground or in the background. One thing, I can get a spectrum and a redshift for it. If it is redshift is very high, then I throw it out. I don't consider it as part of the cluster. But maybe it is just lying a little bit behind or a little bit forward and comparable to the peculiar velocities relative to the redshift. Then you get mixed up. That's okay. Okay, but you cannot get an artificial cluster like that. The probability of getting 10 galaxies all at 10 different distances, all lined up like this and looking like a cluster, is very, very small. So you may have, out of 10 galaxies, maybe 1 or 2 don't belong to the cluster. That's all right. But the probability that there is no cluster and there are 10 galaxies at different distances is virtually zero. It is very reliable. Which one? Estimation of what? No, this surface density, etc., is the galaxy density, not the stellar mass density. It is the number of galaxies per cubic megaparsec or cubic. So see, what can happen is, when you are very close to a very big bright object, then if you take the nearest neighbor, then you are very much biased by that object. But the fifth, so you're biased by outliers. So for example, if you want to measure the height of students in a class, right? If you take the height of the tallest student and say this is the typical height, that is not very representative. So what you will do, you'll take the fifth tallest student, seventh tallest students. You don't go to the bottom. You don't take the average or below the average, etc., because those galaxies are fainter, harder to measure, etc. So that's all. So that's just a convention. As so long as everybody follows it uniformly, it gives you good results.
The RAT and the date is.
Huh.
I have the RAT and date.
Yes.
Then I can plot them in 3D.
Yes. Yes.
And the actual density.
Yes. In a cluster, you will find that the Z is almost the same.
The actually projection is not. If I plot in 3D, the
Z will be slightly different. Yes, but see, remember, you can't. There is a degeneracy between the peculiar velocity which in a cluster is of the order of 1,000 kilometers per second, and the redshift. So what you are seeing is the projection of the peculiar velocity plus the cosmological expansion together. You cannot disentangle the two. You have some estimate of what it is, what value each of these can have, but you cannot, for nearby clusters, you can't tell this much is peculiar velocity and this much is the cosmological redshift. God knows what it is. So that is why you don't try to overthink this and do very precise three-dimensional calculations.
So for the nearest galaxy, 0.1, 0.2.
Yes.
This range we are high with the projection.
Yes.
But after like 0.4.
Then you give up anyway, because all of these things are done. So all of the Dressler clusters were at redshifts up to 0.2 or so. Yes. It's very small. See, if you look at it this way, then the size of the cluster, even at low redshift, the size of the cluster is quite small. So the cosmological redshift of a galaxy which is on this side of the cluster and on the other side of the cluster, is that difference is very small. What is major? Yes, but that doesn't matter unless it's really at 1 or 2 megaparsec. Once you go to 20 megaparsec, 100 megaparsec, 200 megaparsec, 1 megaparsec is a very small distance. Right. Okay. He found strong dependencies of the fraction of spirals, fraction of ellipticals, and projected local density. In poor clusters, the trend is stronger with local density than with simple cluster radius. People said, no, this is not a correlation with density, but it's just a correlation with distance from the center. And then there have been a lot of papers in the literature debating this. Now people seem to have agreed that it's mostly the density which matters. The dependence of FS0 is weaker than FE and FSP. The effect occurs in regions of sufficiently low density that gas stripping or encounters cannot operate. He claimed that the primary effect is with local galaxy density, not cluster radius. The effect occurs at galaxy formation and is not an ongoing evolutionary process. So he claimed in this paper, and it's a very nice paper, this is real, it's there, it's universal, and it's an effect of the early process. So in fact, this kind of thing were this paper was one of the early indicators that some kind of top-down galaxy formation is happening. Which means the most massive galaxies that we see today are the oldest ones. They formed first at the highest density cusps in the dark matter density, and then the lower masses galaxies formed. The origin of this morphology density relationship, there's a lot of debate. Okay, high densities inhibit so what is the origin of this kind of dependence? Some people say that high densities inhibit the formation of spirals. Okay. Spirals may be stripped of gas to make S0s. So maybe there are galaxies, they started off as spirals when they started falling into the cluster, but they got stripped of gas when they fell in. Bulges may grow by the accretion of dwarfs. So maybe these galaxies which are in the central regions are swallowing up a lot of dwarf galaxies and building up their stellar masses. S0s may not be a homogeneous class. Some originate as spirals, others not. Stellar mass is important. So now a lot of studies seem to indicate that S0 galaxies which are low mass are derived from spirals, and S0 galaxies which are high mass are derived from ellipticals. So how do you make an elliptical into an S0? You have a transfer of angular momentum. You have a merger with the galaxy which helps it build a disk, a fast rotating disk. How do you transform a spiral into an S0? Ram pressure stripping can effectively take out the gas from the galaxy and give it. There is a phenomenon which operates in clusters, which is called harassment. Moore et al. 1996 can resemble. So this is basically rapid gravitational shocks which disturb the spiral structure and heat the disk stars. So by heat, one means kinematically change their orbits in such a way that the disk becomes thicker, the rotation speed reduces, and the entropy of the disk increases. And all of these result in a destruction of the stable spiral pattern. S0. It'll make the spiral arms will fade away, star formation rate will go down, and spirals will transform into a disk galaxy like S0. It's not the same as that pressure system. It's different. This is due to frequent encounters, high velocity encounters in the central regions of galaxies. You can imagine at the near the center of a central region of clusters. You can imagine near the center of the clusters, the velocities are going to be very high, right? Galaxies are going to be moving very fast, and the density is also higher in the near the core of the clusters. So the probability of a fast encounter is quite high. By fast, one means both galaxies are moving very, very rapidly. So that is one reason why near the center of a cluster, you often don't have mergers happening now, unless it's a very low mass thing. You have lots of fast encounters, wherein the two galaxies pass each other very quickly. They don't merge, but they affect each other's star formation properties or morphology quite quickly. Sorry? Yes, so you can see evidence for fast encounters, definitely. You can actually see the evidence for the transformation because that happens over 100 million years. Yes. So ram pressure stripping is one of the effective ways of reducing star formation in spiral galaxies. It was the first paper, seminal paper is by Gunn and Gott, 1972. So this refers to the stripping of the interstellar medium due to ram pressure as the galaxy moves through the intracluster medium. We can measure a quantity which is known as the H1 deficiency, which is defined like this: M minus this average M over M average, where M average is the mean H1 mass of galaxies of the same Hubble time. Okay, so this is the mass of H1 that you measure for your galaxy, and this is the mean for that type. So if you have a spiral galaxy, you take the mean mass of spiral galaxy and subtract. H1 deficiency is found to increase towards the center of clusters in richer clusters of higher X-ray luminosity. However, whether this is sufficiently efficient is unclear, because whether it can completely stop star formation or not, or only in the long term, that part is unclear, because studies show that CO is not removed. The carbon monoxide, and therefore the associated molecular hydrogen, is not removed, because that typically sits in the deeper potential, in the denser areas. That remains. So the star formation may not be quenched immediately, because the immediate precursor of star formation, which is the molecular cloud, that is not destroyed. But the atomic gas, which is continuously replenishing the molecular cloud, that is destroyed. So right now, star formation may go on as usual, but a gigayear later or something like that, it will stop. Higher X-ray luminosity is usually associated with more massive clusters, with larger clusters. Yeah. Right. And also the only outer H1 is stripped. So if you look at H1 maps of galaxies in Virgo cluster, you'll find that galaxies near the center have very small H1 cores. Only H1 is there only near the center. And as you go further out, there is more H1 is more distributed. So again, this is a manifestation of the deeper potential near the center. H1 from the outer regions can be pulled out more easily, and that is what is happening. Okay, so with the Hubble Space Telescope, we could do more. Okay, so all of this, as I said, can only be done for clusters at low redshift. Whatever Dressler did, etc., can't be done at high redshift. Galaxies are too small. You can't make out the morphology, etc. But with HST, you can extend the study not very much further, but up to redshift 0.5. And we want to do this because we want to study whether the morphology density relation comes from galaxy formation or galaxy evolution. So this kind of debate will be there in many questions in galaxy evolution. Is it nature or is it nurture? Which means, is this property dependent on the initial conditions, or is it dependent on the subsequent nurture or evolution? So HST studies find that fraction of ellipticals is same as low Z. Fraction of S0 is lower by a factor of 3, and fraction of spirals is higher by a factor of 3 at higher redshift. And the morphology density relation is absent in irregular clusters. These irregular clusters are clusters which are still merging or still forming, etc. So what does this imply? Bullet point 2 and 3. Yes. You look at the next bullet point also. Something is lower and something is higher by the same factor. What does that imply? Yes. So spiral galaxies are turning into S0s as you go further in time. So this may be exactly this kind of ramp pressure stripping operating, which is transforming spirals into lenticulars. What do we know now about galaxy evolution in clusters? First of all, these ellipticals formed earlier because the fraction of ellipticals does not seem to be evolving. So probably ellipticals formed at redshift 1 or even earlier. For ellipticals, the density at formation is most important, not what happened later on. Spirals are converted into an S0 in an ongoing process which depends on density. Some combination of stripping, mergers, harassment, etc. must be active. This is an active area of research with many details still to be worked out, and this outline that I've given is a sort of simplified picture of the reality. Yes. Yes. So in the clusters, it is quite hard to transform an elliptical into an S0. It is in clusters, it's easy to transform a spiral into an S0. But outside, in groups and in the field, where A, the encounters are less frequent, and B, the encounters are low velocity. So the probability of a merger happening is higher because things are moving slowly across each other. They're not zipping past like in clusters. So, so all of these things play a role. So now a broad picture of galaxy evolution has emerged, but there are many gaps. There are many questions that still need definitive answers. What is the role of feedback processes, supernovae and AGN? How do stars in the late stages of life evolve? So when we talked of stellar population synthesis, I said that the modeling or the understanding of post-AGB evolution of stars is still quite uncertain. There are many questions there, and that can affect the amount of feedback and so on. And how much does obscured star formation contribute to the luminosity density? Again, here we are very biased in our observations. We cannot see observed obscured star formation easily because it's hard to see in the optical. And our telescopes are most advanced, most powerful in the optical. Only with the advent of ALMA are we beginning to discover this hidden universe. And what is the nature of dark matter and what role does it play? Is it in compact objects? Is it in particular subatomic particles? All of that will affect galaxy evolution. Yeah, so I will stop here.